A cable of negligible mass stretched symmetrically between two identical trees. A backpack full of books hangs at rest in the middle of the cable. I wonder what tension force there is in those cables supporting the backpack. Well, what I think I'll do is draw a free body force diagram illustrating the tension forces and the weight forces acting on the backpack. And then, to make it simpler for myself, instead of adding vectors in multiple dimensions, I'm just going to use the rule of collinear vector addition, where I can add vectors together that are lying on the same line. A collection of vectors all lying on the same line. So let's see, I'm going to use blue to decompose this first force vector along this horizontal line to about here. And then I'll use red to decompose that first force vector along a vertical line to about there. And I'll label those things appropriately, like this would be the tension force in the first vector in the x dimension, horizontal dimension. And the red one is going to be the tension in the first vector in the y dimension. Now, of course, those red and blue force vectors don't really exist. They're mathematical abstractions. That first tension force vector, this one, that one really exists. That's the electromagnetic force, those, the molecular chains that hold the cable together. As I stretch them with the backpack's weight, they electrostatically hold together and don't pull apart. So that tension force is a real electromagnetic force. But these blue and red decomposed forces are mathematical abstractions I can use to make sense of that diagonal tension force. So now I'm going to decompose the tension 2 into a blue horizontal and a red vertical. I'm going to label those things as like tension 2 in the y dimension, and then tension 2 in the x dimension. And that's going to allow me to do is to apply a collinear vector addition algorithm to this problem. So the two red vectors are going to add together with the vertical weight force vector, this one, and the two blue vectors will add together with themselves. So let me take this and shrink it a little bit, move it over here, and let me get this guy out of the way, like that, and then apply Newton's second law of motion in equilibrium form to this particular problem. So all of these problems should start with us writing down Newton's second law, sigma f equals 0. Now, it's the law of acceleration, so another way to write it is sigma f equals ma, but since the acceleration is 0, this whole term goes to 0. So I'm just going to write sigma f equals 0. That's a statement of equilibrium. All of those forces, those three tension forces, have to act together to equal 0. And then, as I was saying earlier, we don't want to add these vectors in their diagonal forms. We want to do them in their collinear form. So let's now separately write the sum of forces in the horizontal dimension. And hey, you know what? Because I can, let's use blue. There we go. The sum of forces in the horizontal dimension must add together to be 0. And then looking at that, well, let's just show you the other side as well. On the other side, we're going to consider another collinear vector sum, the sum of forces in the y dimension, equaling 0. So now let's follow the rule. This thing is telling me to sum up all of the forces and their x components and set them equal to 0. Now in black there's 1, 2, 3 different forces on the free body diagram. So I'm going to put placeholders for each of them. Tension 1 in the x dimension plus tension 2 vector in the x dimension plus the weight force vector in the x dimension. Those have to add together to be 0. Now, looking at the free body diagram, I see that the tension 1 in the x dimension points to the left, so I'm going to use a negative sign to indicate its direction. Its magnitude is tension 1 in the x direction. Tension 2 points in the rightward direction, so it's plus tension 2 in the x dimension. And then the weight force doesn't have any x dimension, it pulls straight down, so that part's 0. So those two vectors, the two tension vectors in the horizontal dimension, add together to be 0. Doing some algebra, cleaning this up a bit. T2x, the pull to the right, equals the pull to the left. Now, I removed the vector notation. There's no more vector notation on top of these things. I was showing the direction of the vectors with these plus and minus signs, and then the symbols themselves, T1, T2x, represent the length of those blue horizontal components of tension. So the angles given to us in the problem are here. Whoa, nearly. Hold on. These are the angles. And they're the same, they're symmetrical. So since the blue vector components are close to the angle, I'm going to use a cosine. I can rewrite T2x as the hypotenuse T2 times the cosine. Let me do it like this so I can color code it. There's T2, the real length of T2, times the cosine of theta. And that's going to equal the real length of T1 times the cosine of theta. And the result of this is, since cosine theta and cosine theta on each side of the equation, they're equal to each other, I can divide them out and show that tension 2 is equal to tension 1. Now that's because of these angles being symmetrical. Only when those angles have the same value can I divide out the cosine functions. That's an interesting result. It lets me know that whenever there's symmetrical hanging angles, the tension in one cable will be the same as the tension in the other. And it also tells me that if I find the tension in one of the cables, then instantly I have it in both of the cables, since they're the same. However, this equation, this process that we've gone through, doesn't tell us what the actual tension value is, because the function with the angle in it divided out. So what we're going to do is look over here, look at the other dimension. So let me make myself a little bit more room and try it again. Let's work with the horizontal dimension. So I'm summing up the forces in the vertical dimension and setting them equal to 0. The instructions with the sigma f sub y says add up all of the forces and their y components. So just take a moment to do that. There it goes. There's tension 1 in the y dimension, which is a vector, plus tension 2 in the y dimension, which is a vector, plus the weight force in the y dimension, and set that equal to 0. So it's similar to what we did with the horizontal blue vectors. I'm going to remove the vector notation in the next line and then look at the free body diagram to show, to determine what direction the vectors go. So T1y. T1y is right there. So I'm going to, you see it's positive, it points in the upward direction, so I got plus T1 sub y. T2y is similar, it points upward, 2y, 2 sub y, and then the weight force is the one that points down, so I put a minus sign, and then I'm just putting mg, all of mg. There's no need to put subscript y anymore because the entire thing points down, and then those three vectors add together to be 0. It's important that you remove the vector notation in this step because the directions are indicated by the plus and minus sign in one dimension. Alright, so let's continue on. The two y components, those sides are opposite, far away from the angle. So I'm going to use a sine function to determine their length. So it's the hypotenuse, t1, times the sine of theta, plus the hypotenuse, t2, times the sine of theta. And then, just to make it simple, I'm going to put the mg, the weight force, on the other side, equals mg. And that's a nice statement there, I think. If I look at the free body diagram, as I want you to do, I can see the this y component, this y component, and that y component. Well, having some drawing technical issues, but the two y components there point up, they add together to equal the weight force pointing down. The backpack is in equilibrium. And this is the mathematics telling us that. Our goal is to figure out what the tension is. What is the value of T1? What is the value of T2? We know that they're the same. T1 and T2 are the same. Here, there they are. They're the same. So now I notice that this T1 sine theta and that T2 sine theta, they are the same. So let's just call the tension T. It's completely legitimate. Once you see that the tensions are the same, just replace T1, T2 with just T. So essentially what we've got here is 2 times the tension sine theta equals mg. That's a big deal. That this term and this term are the same term. I can add them together and get 2 times one of those terms. And in doing that, I figured out a symbolic expression for T in terms of all these things that I know. The mass of the backpack, the gravitational force field that it's in, and any hanging angle I'm interested in calculating the tension for. Ding, 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 big deal. So let's now finish the algebra. I'm going to divide both sides by sine theta and divide both sides by 2 and come up with an expression T. The tension in each of the cables is equal to the weight force mg divided by 2 sine theta. That's a big deal. That's a big deal. It's a big deal because it allows us to predict the tension for any of the angles that the backpack could possibly hang from. Let me write this down here. Tension as a function of mass and hanging angle. Alright, let's consider calculating some of the tensions at a variety of angles and see what we come up with here. Like one of the most interesting ones, I think, is when the cables hang perfectly vertical at 90 degrees, when there's a 90-degree angle in between the tension force, the tension in the cables, or the cables themselves and the horizontal. That's when the cables are straight up in the air like this, and like this, just totally parallel to each other. Here, I'll try to draw some parallel lines. Straight up. Yeah. Well, imagine the cables are hanging vertically. So in that case, we apply the 90-degree angle to the sine function, and the sine of 90 is 1. So if we look at the tension in the cable at 90 degrees, theta equals 90 degrees, then we end up with just the weight force divided by 2, and that each of the cables holds half of the tension. And the weight force itself is around 76.9 newtons, so divided by 2. Clickety clackety. 38.5 newtons. 38.5 newtons of tension. That's what each cable holds, or maintains, or supports. Tension in each cable. Now when the tension, what's the tension when the cable hangs at a 50-degree angle? So it's spread out a bit. So then I'm just going to write down tension in the cable when theta equals 50 degrees. So now it's mg over 2 sine 50. That 1 over the sine of 50 is about 1.3 or so. So that turns out to be 50.2 newtons. That's the tension at 50 degrees.
Okay, sounds good. All right, love you.
The last thing we want to calculate is the tension in the cables when the hanging angle is 10 degrees. Theta equals 10 degrees. And so, we just look at mg divided by 2 times the sine of 10. That equals, I'm coming up with 222 newtons. 222 newtons. Amazing. It's as if the tension is increasing as the hanging angle goes from 90 degrees towards 0. Tension in cable. That's the tension in each of the cables. It's not the tension in the cables or the two tensions combined together in some way. This is the tension in the left cable, 38.5 degrees when it's hanging at 90, and on the right cable, cable 2 is 38.5 newtons as well. And then when you hang it at 50 degrees, the left cable has 50 newtons or so, and the right cable has 50 newtons of supporting tension. And then when you pull them so they're almost horizontal, just 10 degrees above the horizontal, the left cable has 222 newtons of tension, and the right cable has 222 newtons of tension. So it's interesting to ask the question, what do you think would happen if you were to continue stretching and pulling on the cables until you tried to get them so that they're pulled perfectly horizontal, so the hanging angle was 0 degrees, or the cables were parallel to the ground? So let's graph that. Let's graph the trend. I'm going to take a look at this vertical axis here, which will be the tension. The horizontal axis will be the hanging angle. And hold on. So I'm going to have this be the angle, and this up here will be the tension. Hold on, there, here's the tension. I just want the magnitude of the tension, I don't care which way it points, how much tension. And then I guess 0 degrees will be there, maybe say 90 will be here. And what I'm expecting will happen at 90 degrees, we don't get 0 tension, we get just mg, or mg over 2. Ay, ay, ay. So right, mg divided by 2. And then as we approach 0, because the sine function itself evaluated at 0 is 0, the closer we get to an angle of 0 degrees, the smaller and smaller and smaller the sine function value returns. And when you divide by small numbers, you end up with large fractions. So in the infinite limit, as the hanging angle approaches 0, you're dividing essentially by 0, which gives you an infinite tension. So what we should expect to see is some sort of behavior where the tension is asymptotic to the 0 degree vertical line and approaches infinity. And it starts out at 90 degrees, being the tension force to be half the weight. Cool. Okay, so there's an example of how to solve one of these problems based on equilibrium. It starts with a clear free body diagram, which we decompose into horizontals and vertical components. And then we start with Newton's second law of motion in equilibrium form. And don't get confused there. If it's a multi-dimensional diagonal tension force situation, you have to spread it out into horizontal equilibrium and vertical equilibrium. Then just systematically sum up all the forces in their horizontal components, remove the vector hats and show the direction. Do whatever algebra you need to do to come up with some interesting result, like the tensions are equal to each other but unknown. And then in the vertical dimension, sum up all the tensions in their vertical parts, keep the vector hats, remove the vector hats and show the directions with pluses and minuses according to a standard coordinate system, ups being positive, downs being negative. Sort of get rid of the y components and use the sines and cosines as necessary. Do the associated algebra and solving for the variable like tension in question. And then once you come up with some sort of cool function, calculate away. Enjoy.